Welcome to the fifth lecture on sequence of real numbers. Today we will discuss the relation between limits and algebraic operations. So if we consider two convergent sequences, then we have seen that we can add those two convergent sequences. And today we will see what is the limit of the summation of those two convergent sequences. We will also see the limits of the difference between two convergent sequences and limit of the product of two convergent sequences and their division, limit of the division of two convergent sequences, provided the limit of the sequence given in the denominator, that is non-zero. So here is our first theorem. You consider two convergent sequences, and by convergent sequences I means that sequence has limit. So you consider two sequences xn and yn, and suppose this sequence has limit. So limit n tends to infinity xn is a and limit n tends to infinity yn is b. And this theorem says that what is the limit of the sum of these two convergent sequences. So we claim that limit n tends to infinity xn plus yn, that will be sum of the limits of those two individual sequences. So this limit, it should be a plus b. And similarly, limit n tends to infinity of xn minus yn, this difference, it is given by the difference between these two limits. And if we multiply this sequence by a scalar c, by a real number c, then we get another sequence. And what is the limit of that sequence? It is just c times that limit of xn. Okay, so let's prove this theorem. So we just, what is the notion of limit? Let me recall that as n gets larger and larger, this nth term, it should get closer and closer to this value. And in terms of distance, we can say that as n gets larger and larger, the distance between this nth term and this value, that should get closer and closer to 0, and it should approach to 0. So this distance, it is getting closer and closer to 0. It is equivalent to say that this nth term, it is getting closer and closer to this value. Okay, and in terms of epsilon n condition, what we should prove? To prove this limit, we should verify that for every prescribed epsilon, after certain stage, this difference, that should be less than that prescribed epsilon. So let's verify that for every epsilon, we should find a natural number, so that beyond that natural number, all the terms here, this difference between nth term and this value, that should be less than this prescribed epsilon. And to prove that this difference is less than epsilon after certain stage, what we use these given conditions. We will use that limit n tends to infinity xn is a, so it satisfies epsilon n condition, and this limit yn is b, so this b, that also satisfies epsilon n condition. So we can use the fact that as n gets larger and larger, this difference, it is getting closer and closer to 0, and same thing holds true for this difference also. Since this difference, it is less than or equal to sum of these two difference, then we can prove that this difference, it is getting closer and closer to 0 as n gets larger and larger. So in terms of epsilon n condition, what we should verify? That we should verify that this difference, it is less than epsilon after certain stage. If we will write epsilon as epsilon by 2 plus epsilon by 2. So 1 epsilon by 2 quantity is for this difference, and 1 epsilon by 2 quantity is for this difference. And since limit xn is a satisfies epsilon n condition, so for this particular value, there should be some natural number, so that beyond that natural number, this difference, it is less than epsilon by 2. So I should write that there exist nx and ny, some natural numbers, such that this difference, it is less than epsilon by 2 for all n greater than nx, and this difference yn minus b, it is less than epsilon by 2 for all n greater than ny. So it is less than this. for all n greater than capital N, and this n, it is maximum of nx and ny. So using these two facts, we can see that this difference, it is less than this particular value after certain stage, and let's assume that this is the stage, and after this stage, this difference, this distance, it is less than epsilon by 2, and after this stage, this distance, it is less than epsilon by 2. Then if we consider n, that is maximum of n sub x comma n sub y, then beyond this stage, this difference as well as this distance, it is less than so it is less than epsilon by 2, and this is also less than epsilon by 2. So all this together, it is less than epsilon. Therefore, this difference, this distance, it is less than epsilon for all natural numbers beyond this stage, and this is the verification of epsilon n condition. So therefore, by definition, this limit, it is a plus b. And in same way, we can prove that limit of this thing, it is a minus b. So in this case, again, let's consider this this distance, and this is same as this xn minus a minus yn minus b, and we all know that this absolute value, it is less than or equal to absolute value of this plus absolute value of this, though it is difference. But if we consider absolute value of individual things, then it will be something bigger than this one, greater than or equal to this one. And we have control over this distance because limit xn is a. So again, this thing is less than epsilon by 2, and this thing, that is also less than epsilon by 2, same thing. So there exists nx and ny such that the same thing. Yeah. So yeah, and you take n maximum of nx ny, so then beyond this stage, this difference, it will be less than epsilon, and that proves that limit of this difference, it is a minus b. And next we will prove the limit of c times xn, this sequence, it is c times a. So we will consider two cases. Case 1, that c is 0. In that case, we can see that this sequence, this is a constant sequence and 0. Since this is constant sequence, all the terms are 0. So limit of this sequence, that should be 0 in this case. Next, consider case 2. C is non-zero. Then if we consider this absolute value, then it is something positive, because c is non-zero we are considering. And we again want to verify epsilon n condition. So we want to prove that for any prescribed epsilon, this distance, that should be less than epsilon for beyond certain stage. Okay, so after some values of n. So this distance, it is same as absolute value of c times absolute this distance between xn and a, and we have control over this distance because limit xn is a. So this value, it is getting closer and closer to 0 as n gets larger and larger. Therefore this distance, it is getting closer and closer to 0. Okay, so epsilon n condition we should verify. So we should prove that this is less than epsilon. Why? So since limit, I should write here, so since limit xn n tends to infinity is a, there exists n such that this distance xn minus a, it is less than epsilon by mod c, absolute value of c. So since this thing is positive, if you consider this quantity epsilon by c, this is some positive real number. So for this positive real number, since limit xn is a, for this positive real number, there should be some natural number. Let's say it is n, such that beyond that n, this difference, this distance, it is less than that prescribed quantity. So it is less than epsilon by c for all n greater than n, and therefore this distance it is less than epsilon for all n greater than n. Therefore this value c times a, it is satisfying that epsilon n condition. For every epsilon one can find a natural number n such that beyond that natural number this nth term difference or distance between this nth term and this value it is less than epsilon. Okay. So therefore limit n tends to infinity c times x, and this sequence it is c times a. Next we consider product of two convergent sequences. So if you consider these two sequences again, and then we can consider their product, this product sequence. Now this theorem is saying that if these two are convergent sequences, then their product that is also convergent sequence. And what about their limit? So if limit xn is a and limit yn is b, then limit of their product that should be the product of the limits. Okay. So limit n tends to infinity xn times yn, this sequence it is a times b, and let's verify this. So again we want to prove that this distance it is getting closer and closer to 0 as n gets larger and larger, and in other words we should say that this nth term it is getting closer and closer to this value as n gets larger and larger. So we should verify epsilon n condition. Okay. So we should write that for every epsilon we should be able to find a natural number n such that beyond that natural number this distance it is less than epsilon. To prove that, what we do, we use one fact that since xn is convergent, this sequence xn it is bounded. So that means there exist g and capital G some real numbers such that all the terms lie in this range. And if we draw the picture here, so from here we can conclude, so this thing holds true for all n in the set of natural numbers, and it is equivalent to say that there exists a positive real number m such that this absolute value of nth term it is less than or equal to m for all natural numbers n. Okay, and how to see that? So let's consider this real line, and suppose this is the real line, and here you have origin, and so if everything is on the positive side, you can clearly see that there exists a positive real number such that this absolute value it is less than or equal to m. And suppose you have some portion in the negative side, some portion in the positive side. So what you can do, that if you consider absolute value, then so absolute value, so if xn lie here, then absolute value of mod as absolute value of xn it will be less than or equal to this positive quantity. So one can take this thing as exercise, that if xn lies in this range for all n, then you can find a positive real number such that absolute value it is less than or equal to m. So I should take this particular thing. So suppose xn lies in this range. So this is your g and this capital G, and xn lies here for all n. Okay, and then if you consider absolute value, you should it should lie here, and what in that case it will be something here. So this quantity it will come here, and this one it will come here. So it is mod xn will lie here. If xn lies here, then mod xn will lie here. So in that case this value so this real number, one can take this one as m, and then absolute value of nth term, it is less than or equal to m for all n. So one can take this thing as exercise. One can prove that if xn is convergent, then xn is bounded and there exists a real number m such that this absolute value, it is less than or equal to that particular real number for all natural numbers n. Okay, and then we will use this fact to prove that this distance, it is less than epsilon after certain stage. So we will use again these two limits, and these two limits, they satisfy epsilon n condition. We will use that. So this distance we can write in this way. We can subtract and add this value. Okay, so then it is less than or equal to absolute value of this thing plus absolute value of this. But absolute value of this thing we can write in this way. We can take common xn, and then it is distance between yn and b, and then for this one we can take common b, it is absolute value of b, and times this distance between xn and a, and we have control over this distance. We know that for all n, this value, it is less than or equal to some particular real number. So it is m times yn. Ultimately we should prove that this distance, it is less than epsilon. So for that, what we do, again we consider these two cases. Case 1, that b is 0. So what we do, so if b is 0, then we don't have this thing. So we have only this one, and in that case what we do, that since limit of yn is b, so b satisfies epsilon n condition. So for in that case we consider it is m times by m, it is less than epsilon, and in that case there exists n such that I should write n sub y such that this yn minus b, it is less than epsilon by m for all n beyond this natural number. Okay. Yeah. So then this, so since this distance, it is less than epsilon by m for all n beyond this natural number, we can see that this quantity, it is less than m times this value. So this all together, it is the same as epsilon. So ultimately we have that this distance, it is less than epsilon for all n greater than this particular value. So in that case also, this 0, it satisfies epsilon n condition, and limit will be 0 in that case. And now we should consider case 2, that b is non-zero. In that case, mod b, it is some positive real number. Okay, and in that case what we do, we should use both the limits. So this one as well as this one, and both should satisfy epsilon n condition. So for this distance, we should take that it is plus mod b times epsilon by mod b. We should take epsilon by 2 mod b, and here also we should take 2. So in case 2, we should take this value. So our ultimate goal is to prove that in this case, this distance, it is less than epsilon after certain stage. So what we can see from here, that this distance, it is less than or equal to this value. We have control over this distance and this distance in condition. So for this limit, what we do, that for this particular quantity, we can find a natural number, let's say ny, such that, so in this case, again we should write this. So now I am proving this case 2. So in this case, we consider this particular positive real number. So for this particular positive real number, there should be some natural number such that for all natural numbers beyond that, this distance it is less than that prescribed quantity, and therefore this whole quantity it is less than m times this quantity, and all together it gives epsilon by 2. For the same reason, since a is the limit of this sequence, a should satisfy epsilon n condition. So for that we consider this particular quantity. This is some positive real number. So for this positive real number there exists nx such that this distance it is less than epsilon by 2 mod b for all n greater than n sub x, and then you set n, that is maximum of x and ny. So if you set n, this natural number, it is maximum of nx and ny, then this quantity it is less than this, and this quantity it is less than this. So all together we are getting epsilon by 2 plus epsilon by 2. So all together it is giving epsilon. So we can see that this distance it is less than epsilon for all n. I should use different color, for all n beyond this natural number n. What is n? It is maximum of n sub x, n sub y, and there exists nx because limit xn is a. So for this particular quantity there exists some natural number, so that this distance it is less than that particular quantity beyond this natural number. Okay, and for this particular quantity there should be some natural number, so that this distance it is less than epsilon by 2m for all n greater than ny. Okay, so all together we are getting that this distance it is less than epsilon beyond certain stage, and therefore limit of this thing it is a times b. Consider division of these two sequences. So we prove that limit n tends to infinity xn by yn it is a by b, provided this limit b, that is limit of yn, this thing is non-zero. And to prove this limit we will use this statement 1. So we will use the fact that limit of product of two convergent sequences, it is the product of the limits. So in view of this statement, it is enough to show that limit n tends to infinity 1 by yn, it is 1 by b. If we prove this thing, then using statement 1, limit n tends to infinity xn by yn, we can write in this way, limit n tends to infinity, it is xn times 1 by yn, and then we can use statement 1, limit of xn it is a, and if we prove this one, limit of 1 by yn it is 1 by b, then using this we can have limit of this product it is a times 1 by b, and all together it will be a by b. Okay, so let's prove this one then. And to prove this one, again we should verify epsilon n condition. Some facts that since the sequence yn converges, it is bounded, and in that case also you can find a positive real number delta such that this absolute value it is greater than delta. So this thing I should give it as exercise, that since b is non-zero, prove that there exists a positive real number delta greater than 0 such that the absolute value of yn, because b is the limit of yn, so since if this limit is non-zero, one can prove that there exists a positive real number delta such that mod yn it is greater than delta n condition. So since b is the limit, b satisfies epsilon n condition, and using that one can find a positive real number delta such that absolute value is greater than delta, then this absolute value it is less than 1 by delta. Therefore, this distance it is just this one, and we can write, so we can take this thing out. So it is 1 by mod yn times 1 by mod b times this absolute value, and this quantity it is less than 1 by delta, and this is same as this. So we have control over this distance. Okay. So since b is the limit of yn, b should satisfy epsilon n condition. So what we do that we should, so ultimately we should prove that this distance it is less than epsilon after certain stage. So for a positive epsilon, if you consider this quantity that is also positive, and since b is the limit of yn, so for this positive quantity value there exists a natural number n such that this distance yn minus b it is less than delta times mod b times epsilon for all n greater than n. Okay, and then once we have this inequality for all n greater than n, we can see that this quantity it is less than epsilon for all n greater than n. So ultimately this distance it is less than epsilon for all n greater than n. So for every epsilon we can find a natural number n such that this distance it is less than epsilon for all natural numbers beyond that. So 1 by b, that is the limit of this sequence. Okay. And next we should see some example. So whatever theory we have proved, using that let's prove that limit of this sequence it is equal to 3. So it is some complicated sequence, but we can use the facts we have proved. So this term, this is the nth term of the sequence. This term we can write in this way. So both numerator and denominator we divide by n square, because limit of these things it is easy to find. Okay. So after dividing a numerator and denominator by n square, this term it is same as this one, and we can easily find the limit of this as well as limit of this. So first we should find that what is the limit. So limit n tends to infinity 1 by n square, what is that? It is one can think it is sum of two sequences. So this is constant sequence, so its limit is 1. So this is 1 plus this one again, so directly one can verify that this limit is 0, or in other words using the theory again we can split it as product of these two sequences. So 1 by n square we can write 1 by n times 1 by n, and then this limit it is same as limit of 1 by n times limit of 1 by n, and we all know what is limit of 1 by n. So it is 1 plus 0 times 0, so altogether it is giving this value 1. And similarly we can prove that limit n tends to infinity, this one what we can do, so this is limit of 3 plus limit of n tends to infinity, so it is just this scalar times 2 times this sequence, so we can write it plus again limit n tends to infinity 1 by n square, this value. So this is, so again this constant sequence. So for constant sequence it is convergent and limit is this constant, so it is 3 plus 2 times 0, because limit of 1 by n is 0, and again we have already, so we already know limit of 1 by n square, that is also 0, so altogether it is giving 3. So then, since this limit it is 1, it is something non-zero, it is something non-zero. So using the rule of division, we can see that limit of this sequence divided by this sequence, it is just limit of this sequence divided by limit of this sequence, because limit of this sequence it is something non-zero. So this thing we are getting, it is limit of 1 by n square. So this is 3 by 1, this is 3. Okay. And so here are some more results. So if you consider a convergent sequence, so let's say xn is a convergent sequence, that means it has a limit, and suppose a is the limit. So limit n tends to infinity xn, that is a. Then what can you say about this thing, limit of this absolute value? So you can consider this sequence whose nth term is given by the absolute value of xn. For example, if you consider your sequence is this, so nth term is minus 1 power n, then this sequence, that will be this one, and it is just constant sequence. I should write here, this is constant sequence. Okay. So anyway, so here it is saying that if xn is convergent, then what can you say about this sequence? So I claim that in that case, this sequence, that is also convergent, and limit n tends to infinity, this mod xn, it is just mod of a. So mod of this limit. Okay. So it is just saying that limit provided this limit exists. So this is the given condition, and let's verify that this sequence is convergent and mod a is the limit. To prove that, this is the observation, we need to prove that as n gets larger and larger, this distance it is getting closer and closer, and it approaches to 0. So we should verify epsilon n condition. So we know that this distance it is less than or equal to this distance, and we have control over this distance, this absolute value, because a is the limit of this sequence. So a satisfies epsilon n condition. So for every positive real number epsilon, there exists n, a natural number, such that this thing is less than epsilon for all n greater than n, and therefore this absolute value it is also less than epsilon for all n greater than n. So for every epsilon we can find a natural number n such that this distance it is less than epsilon for all natural numbers beyond that. So this thing it is satisfying epsilon n condition, and therefore this limit it is just this mod a, and it proves this theorem. So here it is saying that if some sequence is convergent, then the sequence of this absolute value this also convergent, and limit is given by this thing. But what about converse? So suppose you have a sequence, you don't know whether it is convergent or not, but it is given that this sequence of absolute value, this is a convergent sequence. Then can you say that this sequence is convergent? So answer is no in general. So for a sequence xn, if sequence of this absolute value it converges, then it does not necessarily imply that this sequence converges. Example given, that you consider this sequence, it is alternating thing. So minus 1, 1, minus 1, 1. So this sequence is not convergent. It is not converging to a particular value. So we say that it is divergent sequence. So this sequence it is not convergent, but if you consider this sequence of absolute value, it is constant sequence and it converges. So it converges to 1. If sequence of absolute value converges, then you cannot conclude whether this sequence converges or not. However, if this sequence of absolute value it converges to 0, then you can say that this sequence it converges to 0. So this is an exercise that for a sequence xn, if sequence of this absolute value it converges to 0, then this sequence that is also convergent sequence and it converges to 0. So one can verify that, one can prove that. I'll give this thing as exercise. And here is an example. So if you consider minus 1 power n divided by n, it converges to 0 because its sequence of absolute value, it is just this sequence whose nth term is 1 by n. This sequence it converges to 0, it converges to 0. So one can prove this thing, this exercise. I'll stop here.